Hello everyone, this is the review video for STAT 2810, sections 106 and 109. This is our skills review. So I'm going to go through some of the tools that I think would be helpful on the test coming up Friday, and we'll move on from there. So I had a lot of questions about the residual stuff. So I thought I'd start out just by doing the basic correlation stuff. So what I've got here is I've done in Excel, I've started with just x 1 to 30. Then I did x plus a small random error. And this will get me some scatter plots going that do actually have some variability to them. So what I'm going to be doing is plotting this column versus these columns. So let's just start out simple. We'll look at this linear version. So I'm going to skip the scatter plotting step because this is kind of simulating a test. In general, I'm not going to give you data sets that you have to confirm are linear before you go forward. So I'm going to go straight to calculators. No, I'm going to go straight to stat, regression, simple linear. And I'm going to start with just x versus the y equals 4x variable. And so if I do that, and while we're at it, I want a histogram of the residuals and a residuals versus x values. Oh hell, we'll take QQ versus residuals too. And this will be able to, we'll be able to start comparing residuals here. So there's our summary. Our R is very good. And let's look at the scatter plot. Yeah, our R should be very, very good. Since this is a linear equation with just a little bit of bouncing in it. Note also there's no guarantee how many points this line is going to pass through. Here's a histogram of the residuals. This is interesting right here. There are 9 residuals that are at -5 or so, between -6 and -4. Well guys, it happens sometimes when you generate random numbers. Let's look at this though. Okay. So this is QQ versus residuals, so the normal kind of distribution of residuals you'd expect, and then this. Let's check x values versus residuals. Okay, so we actually know that this is random variation here because I made it that way over here. I have an Excel document where I made a random number. So you see there is a gap in the spread. The gap is right here. But in general, very random looking. Let's compare this. So let's look back through. There's our histogram of residuals. There's our fitted line. Looks very good. You know, there's some streakiness here, but it's not huge, right? Let's look at something that really does have a non-linear aspect to it. So stat, regression, simple linear again. Still picking x for my variable, but my y variable is now going to be x squared. Still getting the fitted line plot, still getting histogram of residual, whoops, still getting fitting line plot, still getting hold control or command if you're on a PC for this, histogram residuals, QQ plot, and residuals versus x values. Okay, calculate all that. Correlation still isn't too bad. Let's look at what's going on here. So keep in mind that we're plotting kind of the linearist bit of an exponential equation. If I plot one in Desmos real quick, what you see so we are plotting between like 1 and 30, right? Between 1 and 30. And yeah, it's kind of linear between 1 and 30. Let me set my bounds, my x. 1, 30. I should go from 0, 0 to, let's do like 400. Okay, so here's my point. So plotting between 0 and 30, there's a huge amount of data points that follow this kind of line up here, right? Let's zoom out even more. Okay, so between, right, I mean, it's zooming up. It's a very straight line, but it is linear-ish, except for this little bit of wiggle down here, right? And we can see that. We can. What happened? Yeah. Okay. We can see that here, right? At the bottom, it's off. It's too high. At the top, it's too low. Or sorry. The top, it's too high. At the bottom, it's too high. At the top, it's too high. In the middle, we're getting okay. And this is, you see that it's curvy. It's bending away from a prediction. What happens to the histogram of residuals? They're a little flatter, almost uniform. QQ plot, can't see much there. Ooh, here's where we see it, right? Big residuals, small residuals, big residuals. Clear pattern, even though correlation coefficient and R-squared were very high. But since we looked at a plot of the residuals versus the X values, we knew that this was not linear. Let's see. Oh, I'm sorry. I plotted this. I was talking e to the X here. Sorry, guys. What was this? This was X squared. There we go. Zoom squared. Okay. Okay, this will make a little more sense now. Sorry about that, guys. Yeah, here's 0 to 30. Yeah, so there's just, it's a bend in it, right? You know there's a bend in it because the residuals were looking bendy, right? They were not looking like that, right? So linear, non-linear. Okay. Let's look at one more, just to whip a dead horse here. Regression, simple linear. Let's go X versus the exponential version. I just want to show you guys this. And I'm going to skip some steps. I'm just going to do the residuals plot here. Okay, so here we have linear with residuals. Here we have quadratic residuals. And over here, these are exponential residuals, right? Wrong. These are wrong. These are so ridiculous, right? Look at, I mean, this, you could almost like maybe pretend this was something else, but this, not linear in any way, because there's this huge pattern emerging and this bouncy pattern emerging in our residuals plot. So that's why you need to plot the residuals. That's why you need to be able to interpret residuals. There's a few more examples of this on starting on page 205 in your textbook. Just a ton of example problems. Look at like 43 cigarettes, 50 interest rates and mortgages. Just plenty of scatter plots to help you train your intuition on these guys. All right. So now I'm going to look at correlation tables. So I picked out a couple problems from the textbook. These are also starting page 208, and I'm going to look at 25 and 26 for starters. Now I mentioned an Excel workbook, and you can compute these by hand. You will have the formulas on the board. There's no reason you can't. But I understand that you guys are under time constraints. So here's a workbook one of my colleagues has made. And you can see you got several options here with what kind of stuff you can do. We'll be working with summary given. We'll be working with probability sheet. And we'll be working with adding random variables. Here's that calculate variance and standard deviation and mean stuff here. Okay, so, but for starters, we're going to go back over to the summary given. And let's see. So on 25 here, let me just... I've been talking for a while. I just want to double check that you guys are seeing what I'm seeing. Yes. Okay. Good to go. And so we see that So in part A, what are we missing? Just the regression equation. So you'll just have to assemble that from the pieces, but the pieces are right here in the list, right? So that's A and B. Let's look at C. C, we're missing the Y mean. So we have to find this one where we're missing the Y mean. Missing the Y mean here. And remember, guys, only enter numbers in white cells, okay? So we have to find the version of this that is missing Y mean and SY only. Y mean, SY only, yes. So that would be, it'd be this one. Yeah, so let's fill that in, right? Oh, I'm sorry. Yeah, this one, right? We want to fill in S mean and Y mean. Okay, let's go for it. So C, I get a 12 for my X bar. So that's my X mean, a 6 for the standard deviation. We've passed these guys. My R value for C is negative 0.8. Intercept, my B0 is 200 for this one. And my slope is negative 4. Boom. And now, here's our values right there. So this might take a little practice to get used to, but I hope that you can see how this could be an advantage. So this is an odd problem. You can check the answers in the back. Let's do one more. So for D, I need the one where I have colored spots for Y bar and R. R, Y bar, and R right here. So now I fill in all the white spots, right? 2.5, hit a tab to get over. 1.2, hit a couple tabs. SY is 100, tab. R, moving on. Intercept, B0, negative 100, tab over. B1, positive 50. Tab over, and now it's going to fill in all my things. So I know my R squared is 0.6. I know my Y bar is 25. So I want you guys to be able to speed up then. This I hope will help you speed up on getting those correlation tables on the test. Okay, so that's correlation tables. I could do several more examples, but it's that simple with this workbook, which I've posted on As You Learn. You'll have it right here. Okay, so there's that. Residuals, we talked about residuals. We talked about making correlation tables so far. Okay, so now we're going to move to talking about some false positives. And I'm going to do 2 examples on this. I know this video is getting long, but I think it's important. Then I'm going to do at least one add random variable, and we'll call it a day. I will either post another video or some materials for studying bias. I'm not sure which one yet. So let's go through it. Where am I? What am I doing? Oh yeah, false positives. Okay, so for these, I've picked out a couple problems from the one problem from the textbook and one I sort of made up. So this is page 380 from your textbook. I wanted to do one where you had all the numbers worked out by hand, because what I'm going to do is not a by hand version. Okay, so tuberculosis, false positives. We saw how bad it was to have, how bad it could be when you were getting false positives in medicine. So here I've set up a Bayes rule calculator. So I'm going to go into the options and edit so it makes sense for our problem. So our problem says our problem starts on the last page. So let me shove stuff over. Yeah, there we go. Here we go. Okay, so please read this problem thoroughly, right? But what do we want to know? What we want to know well, yeah. Here it is. I'm interested in the probability that the author had TB given that he was tested positive, right? So we have the probability that if you have TB, what was the chance that you tested positive? But what we want is the opposite of that, right? So in probability language, what that would mean is that what we have is probability positive test given that you have TB, right? And we want to reverse this. We want to say, well, yeah, but what's the chance that I have TB given that my test was positive? Okay. And StatCrunch has a method for this. I find it easier to use than the test2 workbook method. And remember, you can always draw a tree. Oops. You can always draw a tree. How do I get to the next page? Come on now. You can always draw a tree and do this calculation, right? That is not a problem, right? If I want to reverse a given probability like this, I can do the probability that I have TB and a positive test and draw the tree. I've got it right here for you, and multiply or add those two probabilities together of getting a positive test. So what this is just a shortcut. If you understand that stuff, this is just a shortcut for getting there. So what do we care about in this case? We care about having TB or not, right? So I'm going to say TB, comma, TB not, right? So we're using those chickas for TB. And what's this going to be? Outcome I'm worried about is the positive test. And actually, StatCrunch is really flexible about this. I could write positive test here, and it would be fine with that. Okay, so now my events make a little more sense. So we just need the chance that you have TB and the chance that you don't have TB. Okay, so up top, I'm going to write 0.00005. Okay, on the bottom, I'm going to write 0.99995. Just copying from the problem there. Now we got to be a little careful over here. What's the chance that you had a positive test given that you had TB? I believe that's given for you. So if I had TB, the chance that I have a positive test, actually, just float back over here. I would like to get these straight from the problem. So positive test given that you have TB, and positive test given that you don't have TB. So a positive test given that you don't have TB, that probability is 0.01, which makes this probability 0.99. Now we look over here. We look to this drop down, and we want the chance that you have TB given that you were done a positive test. So there's our probability expression. And boom, it's going to give it to us. It's going to give it to us that it was about 0.4%. About 0.5%. And if I remember that I'm on the page before the actual answer, and I remember that this arrow thingy is funky, and I go down here, and I get 00497. Yay! You guys see that? We won! We won! Yay! Okay. So that is, so we've done 2 examples with false positives on disease yet. But this is not the only case where this comes into play, right? So I've set up another problem up here. I won't need the textbook anymore. Okay, so lie detectors are used often by people that have no idea how inaccurate lie detectors are. Lie detectors are often. Don't use lie detectors. They're bad. They don't show what people think they show. Okay, so we know that if you are lying, a lie detector will detect that about 67% of the time. I've made up these numbers, but they're close to the real ones. The probability that you detect, given that you did not lie, so I'm using that tick mark to indicate not statement, right? Okay, so let's just fill in our table again. Lie and not lying, that's what we care about. And what we care about is that we were detected, right? So the outcome of interest is our detection, right? Because what do we want to know? Chance that you told the truth given that you were detected. In other words, you were not lying given that you were detected, okay? So I've got lie, not lie, and my outcome of interest, detect. Recompute this. Oh, and we need one more piece of information, guys. Somewhere between, I don't know, 85 and 95% of people tell the truth. So we need that probability. So let's call it 90 for this example. So the probability that you're going to lie on a job application is 10%. The probability that you do not is 90%. The probability that you are detected, given that you lied, right? Detect given event is lie because we're in the first row, is 0.67. And the chance that you will be detected even though you didn't lie is 20%. Okay. So 24% of the time, people that are telling the truth are detected as liars. Or more importantly, if you tell the truth during a lie detector test, you have a 24% chance, assuming you're Bayesian, of being called a liar. So there's two examples of using Bayes' rule where you don't have to draw a tree. You just have to know 3 probabilities to get the reversal, right? So I have to know detect given lie, detect given I didn't lie, and the probability of lying, period. If I know those 3 things and their complements, then I can answer the question, didn't lie given detect, or lie given detect, right? So those are the probability reversals there, that Bayes' rule stuff. Okay. I only have one more thing to talk about. And I guess really it's 2 things. There's a probability distribution. Here we go. So there's a probability sheet, right? So let's do one here. This is like a payout, right? So let me see. I thought I had an example for everything set up. Okay, these are going to be easy to find. Okay, yeah, this is example, this is an example on page 392 of your textbook. And we're going to find a standard deviation. Okay. So we have some X's here. So these are outcomes. And so the outcomes are $20 payout on ace of hearts, $10 payout if it's diamonds, then hearts, and a 0 payout if it's a black ace. This is a game called Lucky Lovers Discount. That's actually all I can tell you right now. I just flipped to an example in the book because I thought it would have a good probability distribution for us, and it indeed does. So here I'm going to rate outcomes, right? Little x's are individual outcomes of our big X. Those are the outcomes I worry about. My probabilities, they're 0.25. They're 1/12. And they're 2/3. And boom, it all got spat out just like that. My expected earnings are 5 and a bit, almost $6. The variance in my earnings is $74. Square root that, and you'd get your standard deviation. So I would expect that, 68% of the time I would make somewhere between, I would lose like $3. I would either 68% of the time, using the empirical rule, I would lose $3. I would be somewhere between losing $3 and gaining, adding these 2 things together, $14 or so. So, you know, might not find this game you may not find this game in a casino because the expected value is too high. But there's a probability, simple probability distribution, right? So if it tells you a certain number of outcomes and their probabilities, that's what you do. You set them up in this column and run with it. Now, what if I had a slightly different problem? What if I had a random variable x, for example, with a certain standard deviation and a certain the random variable y, right? So if your list of random variables all have the same x, all have the same mean and standard deviation, then you can just say how many of them there are, the mean and the standard deviation, and it'll just add up that many of them. This is rarely the case, though. In most cases, we're down here where we are adding two random variables, right? And we're doing it by the formula ax plus by, right? So let's do a couple things here. Let's say we have a random variable x and a random variable y, and we have that the expected value for x, that's let's say 5. Why not? And that we have the expected value for y. Well, let's just say that's -2 to keep it interesting, right? Let's say our standard deviation of our random variable x, let's say that's 2.8, just for giggles, and the standard deviation on y, we'll say that's very big. We'll say that's 10, just for because we can. Okay, so the cool thing is if you set it up like this, and let's say the trouble is that x is sales of, say, skirts. And let's say this is let's say this is the theft. All right, so and we'll make it a little bit bigger, -5. We'll say that. Okay, so say you're got a stall and you're selling skirts, but people walk off with them sometimes, and that represents a loss. And let's say it represents the same loss as gaining a skirt. Let's say in general they steal 3 skirts a day, but you tend to sell something like 12, so you make $60. Maybe we'll do something like that. Let's say that could change by 3 skirts very easily, but in general it only fluctuates by 1 skirt, the theft part. Okay, so so now I want to add these together to get my total expected earnings, right? So I'm going to use the 1x plus 1y, right? So my a is my 1, b is 1, my mean of x is 60, my standard deviation in x is 15, my mean of y is -15. And so when I set them up like this, I can just copy them down. You know, it's kind of nice. All right, and here's my new standard deviation and variance. So let's say it's a little more complicated than that. Let's say I realized that my theft was twice as high as I thought it was. So I'm going to have to multiply everything by 2. Now I would change this b to 2, hit enter, and it's going to automatically update everything I just did. So when you're adding two random variables, here's how I would do it. Let's say you only want to add one random variable. Let's say this y crap is not what we're looking for. Let's say we really just only have skirt sales. But what we found is that we're going to do a markup. We're going to mark them all up by 20%. So there's our markup. So now I want to compute 1.2 times x, right? Multiply everything in x by 1.2, not 1.52. So that means my A is now 1.2. My B is nothing. This B is nothing. That B is nothing. And there we go. It's done. It's done for us. You can check things like, does 1.2 squared sorry, hold on. Let's see here. (1.2 squared times my standard deviation squared, 25. What's that equal? Okay, square root that. Oh yeah, so we're in good shape, right? Square rooted my variance, computed the old-fashioned way, and there we go. So that's the skills setup for this week. I know I have a request out there to do a lot of sampling stuff. Here's what I'm going to say. There's very little sampling bias on the test. And I think what I'll do instead, well, I think I will make a video about it though. Sample bias is important. So check this out on As You Learn, maybe practice some homework problems with it, and you guys will be good to go. Thanks so much for listening to this appallingly long video. Have a wonderful weekend.